Hi. This is a talk about 9 years of overlooked MikroTik Pre-Auth RCE. And I'm NiNi Chen. I am a security researcher from DevCore. We are from Taiwan. And I'm also a member of the Belson CTF team and member of Undefined. And the first question is why? Why the router OS? Okay, just as usual, because we want to participate in Pong2On Toronto 2022. As one of the target, the router board of MikroTik hasn't been exploited in the previous event. So you may already know the rules. The participants must find pre-auth RCE without user interaction to acquire the point of the target. And the Soho's mashup, a special category, was introduced in 2022. Participants have to chain routers when exploit and another device exploit to earn the point and the bounty. The bounty and the point in this category is relatively high. So if you want to win, you must get a point of like one Soho's mashup chain. So we started to survey the router board to seek the possibility of pre-auth RCE. And let's recap some basic things quickly. The router board of MikroTik is quite popular. This is not precise, but yeah, it's popular. And the router OS is the operating system of router board hardware. By scanning MikroTik, we can observe about like 3 million devices online. And the router OS is a standalone operating system based on the Linux kernel. It's currently based on the 3.3.5 version. And the MikroTik also offers like an ISO image, so we can run it as a VM. So you don't have to purchase a product. But yeah, there are some constraints we'll talk about later. And it's closed source and also a closed ecosystem. It means everything on the system was written by the MikroTik. And funny thing is that according to the download terms on the MikroTik's website, you have to pay like $45 to get a CD with GPL source code. Yeah, why not? But actually, you don't have to like buy those GPL source code because they are just useless for like bug hunting. And there was a people publish the GPL source on the GitHub. If you can find it by just Google. And most of them are not relative to the core function of the MikroTik. So don't bother to pay the $45. And currently, there are 2 versions of router OS v7 and router OS v6. They should be considered as 2 branches because their implementation are slightly different. And we are talking about the v6 today, but it's not that different from the v7. And there's another download option. It's called Cloud Hosted Router. It's the router OS image for VM. But there's only AMD 64 version is available. So if you want to participate on the Pong2On, you still have to buy one because the product itself mostly MIPS, big endian. And most services on the router OS are implemented by MikroTik themselves, and they all share a similar architecture. So let's call them Nova binary afterward. And they use Nova message to talk to each other. Though the router OS is based on the Linux kernel, users are trapped inside a customized CLI, which is very common. And there's no official method to access the underlying Linux system. And only developers can install a backdoor package to access the Linux for debugging purpose. So the first task for us is to jailbreak. And an administrator can manage their router via the web panel or a special application called the Winbox, which is a Windows GUI application. It's also a popular attack service because the Winbox interface on the router is also a Nova binary, which will forward your Nova message to other Nova binary on the router, even they are not exposed their port to the network interface. So it was popular. And to understand how people research the router OS, let's have a look at past CVE of the router OS. There are a total of 80 CVEs, and 28 of these CVEs are pre-auth exploitable, and the victim is router itself. And 16 out of 28 are those in various components. 8 out of 28 are like DNS poisoning, allow attacker to do MITM, or firewall evasion. Only 4 pre-auth vulnerability in history can lead to a shell or login as admin directly without user interaction, which is the constraint of the Pong-to-Own event. And there are what we are care about. And 3 out of 4 were found during 2017 to 2019. And 3 out of 4 are in the wild. So let's have a close look. CVE 2017-20149, aka Shimei Ray, is one of the exploits leaked from the CIA in 2017. By sending an HTTP request with a crafty content length, we can corrupt stack to execute arbitrary code by stack clash. Yeah, the same stack clash the Orange mentioned yesterday. And CVE 2018-7445 is a buffer overflow in the SMB, and it was found by black box fuzzing. And CVE 2018-14847 is also one of the exploits leaked from CIA. The bugs allow unauthenticated attacker to read arbitrary file on router OS. That sounds not a big deal in the first place, but since router OS implemented almost everything by themselves, including the user authentication. So the password stored on the router OS was just simply repeating XOR your password in plain text with the hash of username plus a fixed string at that time. This piece of code is still in the router OS, but it's not used. It's not using anymore. So the password can be recovered easily, and a bug with arbitrary file reading is sufficient to log in as admin because you can recover the password. And CVE 2021-41987 is a heap buffer overflow in the while the decoding base 64 of the SCEP service. This was discovered on an APT's C2 server in 2021. As we can see, these vulnerabilities are mostly in the wild. We can't learn too much from them directly because no one will explain how they exploit it or how they research this target. So let's take a look at some talks and articles about the router OS. In 2017, there are 3 talks. They are about the packet format adopted from the router OS, the developer's backdoor we just mentioned. Yes, they are helpful to have a big picture of the router OS. And in 2018, a talk analyzed the Nova message in binary and JSON format. There are 2 formats, but they only use the binary format today. Yes, so we'll talk about it later. And introduce how Winbox client talk to the Winbox interface by Nova message. So you can forward your Nova message to any Nova binary. So if they didn't check the privilege, there will be a problem. And they found the post-auth Stack Overflow. And in 2019, the first talk is let's take a look about the MikroTik firewall and net bypass, because the make it run with MikroTik is just the same thing in the previous year. So the MikroTik firewall and net bypass is talk about the vulnerability in the Winbox. They can be used to scan the intranet if the Winbox is exposed to the internet. The next is the finding and exploiting CVE 2018 7445. It found a stack buffer overflow in SMB by black box fuzzing, we just mentioned. And the deep dive MikroTik exploit is a security analyze. Talk about the CIA exploit we just mentioned, how they be used to massive exploit and the exploit events. The next one, help me vulnerability, you are my only hope. Because the leak exploit from CIA has compromised a lot of device, but we don't have a method to check if your device was compromised because you are trapped in a custom CLI. So this talk is released some like post-auth jailbreak tool for you to check if your device was compromised. And the last one, RouterOS chain to root. It's about chaining DNS poisoning and downgrade attack to get a shell. And in the last year, 2022, pulling MikroTik into the limelight, talk about the Nova message and disclose a post-auth vulnerability in www that can be used to jailbreak. And they released a tool to help researchers to quickly get a shell. And we also modify this version because it's based on the AMD 64. We modify this version to the MIPS to get the shell for ourselves for like further debugging. And to here, you can see that it seems like the whole world is talking about the Nova message. And the attack surface about the Winbox is also a part of Nova message. So it seems the whole world is talking about the Nova message in the IPC of RouterOS. So we also try to understand what it is, and based on this, we start to reversing the RouterOS. So let's talk about the IPC of the RouterOS with an example. While a user log in through a telnet to access the console of the RouterOS, the telnet will immediately call execl to execute the login process to ask the user for a username and password. Then the login process will send a Nova message with the user name and password supply to the user process to check if they are correct. The user process also responds in the Nova message. The Nova messages consist of key value pair, and the key can only be numbers. The sys2, the columns, the sys2, and the sysfrom, they are arrays containing the ID of Nova binary and the ID of the handler, which should handle this message. Like if we want this message be handled by the handler 4 of the user, so the sys2 is 13 and comma 4. It means the fourth handler of the user have to handle this message. Okay, the communication between two processes is something like this. Every message is sent to the loader via socket, and the loader dispatches the message to the corresponding binary. So assuming the ID of the login process on the left-hand side is 1039, and the ID of the user process on the right-hand side is 13, and the handler 4 is responsible for checking the username and password. So the login process sends a request with username to the user process. The value of the sys2 means the target is the handler 4 of binary ID with 13. And you don't have to fill the sysfrom because the loader will do that for it. And the next, the loader removes the target binary ID in the sys2, add the source binary ID to the sysfrom, and then forward the message to the target process. When the user process receives the message from the socket, it will also remove the handle ID from sys2 and pass it to the corresponding handler. Then the handler does the rest thing of the user authentication. Yeah, and we just mentioned that the Winbox interface on the router is a popular attack surface. That's because the protocol Winbox client used to talk to the interface on the router is basically a Nova message in the TCP packet. So if the target handler fails to check the sender's privilege, they can cause problem. Yeah, because everyone can send to the Winbox interface. And the message used in IPC is constructed by NV message and the relative functions. Nova message is type key value mapping and can contain various type and also another Nova message. So it can be nested. That's why there are so many DOS in various components, because they fail to properly handle the nested case. And because the JSON format of the Nova message is deprecated, we only talk about the binary format today. The M2 at the beginning is the magic byte for the Nova message. Then it uses 4 bytes to describe a key. The first 3 bytes of key are ID, and last byte is type, and the bytes following are the value for that key. So we can take it like this. The message is ID, types and values look like this. Types like Boolean can be expressed with 1 bit, so they directly using the lower bit of the type bytes. To understand which binary corresponds to the ID in the sys1 or sys2, we need to parse a .x3 file under the loaders directory. It's a kind of XML, but in binary format. If the binary was introduced by installing the packet, its ID is under the loader directory of that packet, like which is this one? Like IP6, yeah. And some IDs cannot be found in the X3 file because the process is not persistent. The ID is just a serial number because when you log in, it spawns a new login process. So that's not persistent. And other binary also have their own X3 files for different purposes. For example, the X3 of www describes which URI should be handled by which servlet. It seems like it's a good target for fuzzing, right? But we can't just fuzz it and expect it we get some like Pre-Auth RCE after 2 months. And it's a spoiler. Oh, we are here, yeah, on the timeline. So when we were writing our exploit with the vulnerability I will introduce later, a talk in the POC 2022, MikroTik router OS security, the forgotten IPC message. But I think it's far from forgotten. The talk is about fuzzing, and the talk is about fuzzing the Nova message. And turns out it found a lot of post-auth RCE. By the number of CVEs, it started from like CVE 2020 20211. So it has been fuzzing for a long time, like maybe at least 2 years. So a bit of an afterthought. I don't think we can write a better fuzzer to get a better result if we do the same thing at the late time. And not to mention, we only have 2 months. So, sounds like, is it still possible to pwn the router OS? Reviewing these CVEs again, most of the vulnerability we think interesting were discovered many years ago. Researchers also found lots of vulnerability, but as we can see, the MikroTik becomes safer and safer. But in 2021, a vulnerability in the SCEP was disclosed by analyzing in the wild exploit on the APT's C2 server. Was it undiscovered until then because it was not a default feature? Or is it just because people have overlooked something? Here is some observation. Most talks and articles focus on jailbreaking, analyzing the in the wild exploit, and a Nova message in IPC. So I have a summary after reading this article and starting to reversing myself, because while we were reversing, we found there are a lot of details was not mentioned on anyone's talk. So it's a brief summary. As no one with sanity, we like to dive into the detail of non-binary because it's just secured by obscure. It's really hard to read. And except for the exploit from the CIA and APT, most of the research about bug hunting is fuzzing the protocol, playing with Nova message, or fuzzing Nova message. By the outcome, it seems like attackers are more familiar with the router OS than us. We need more details about the Nova binary to find another bugs. And don't get me wrong, I don't against fuzzing. I even wrote the master thesis about the fuzzing. But we must ensure we check everything essential to take advantage of the context. I don't think the system is perfect now, but there's a gap between researchers and attackers. So what was missed if we want to find some pre-auth RCE bug in router OS? The first question is, where are the entry points of the customized IPC? Most of them can be only accessed by authenticated users. So we can foresee that playing with Nova message in IPC will result in lots of post-auth RCE, which is not we want. And IPC is just part of the implementation of most of the functionality. We want to review the crucial part directly and carefully. For example, how does the DHCP process parse a DHCP packet to extract the info it needs? Then we have to mention the architecture of the Nova binary. Every Nova binary has a looper, or its derived class. The looper uses poll to check the status of socket and process event in each loop, just like a regular event loop you have seen everywhere. If you ever wrote a game, it's just like a game main loop. And the looper is responsible for the communication between the current process and the loader. The looper registers a special callback for the Unix socket, which is used to communicate with loader. The special callback on message sock will dispatch the message to the corresponding handler once it receives Nova message from the socket. And so how does the handler work? While the looper receives a Nova message, it will dispatch it to the corresponding handler. Look at the right-hand side, the sys2. So if there is no handle number in the sys2, the looper itself will handle that. But if there are some handle number, like if it's 0, the handle 0 will handle this message. And let's assume the handle 1 is responsible for the Nova message. And then it will call a function in vtable with the CMD prefix that corresponding to the command specified by the syscmd. So because the handle is a base class, commands relative to object are unimplemented. The array function on the screen, they are unimplemented because they are relative some about object. The CMD unknown is often overridden and used to extend the customized command. Sometimes the developers override the handle CMD instead of the CMD unknown. There's no why. They just roll it like that. So you have to check two places. And you may have already read some of these in the past research. But most of the time, the Nova binary uses the derived class rather than the best handle class. The derived class can store a collection of objects of a specific type, just like the STL container of the C++. And for example, while the user is setting up a DHCP server on the web panel, that will send a message to the handle 0 of the DHCP process to create a DHCP server. The handler 0, which is an instance of AMAP, is a derived class of the handle class. Call a function on its on its vtable with offset hex7c to create a DHCP server object and insert it into a tree. The hex7c is the offset to the constructor of the inner object. And you can find the offset of such function in other derived classes by just reversing the cmd add object function. You can find the constructor of the inner object of each derived classes. And in the previous example, the web panel sent a Nova message to DHCP to create a DHCP server. But what if I told you that some functionality don't even use the Nova message? For example, the CDP and L2DP. They are implemented in the discover, the binary code discover. The looper registers two callback functions. The looper then keep looking and check the status of sockets. If there are incoming packets, the looper calls the callback function. The callback of CDP will extract the information from the packet and store them directly into another async map without sending any Nova message. So if you play with the Nova message, you will never coverage this code. So we start to review the router OS by enumerating functionality and reversing them by the concept we just mentioned. Then we found something strange, yeah. And this part is nothing to do with everything I just talked. And one day, while plugging and unplugging some cable connected to the router, suddenly the log file showed the RA-DVD crash several times. So we tried to reproduce the crash by just manually plugging and unplugging cable about 1,000 times, but couldn't figure out the crash condition. The condition is still unknown today, and the crash appeared randomly. Instead of mindless unplugging and plugging, we reverse the RA-DVD to see if we can find something interesting or the root cause. We didn't find the root cause of the crash, but we got something better. So what is RA-DVD? RA-DVD is a service about the SLAAC of IPv6. Let's say a computer or a node want to get an IPv6 address. It will first multicast a router solicitation to all router asking for a network prefix. Then if a router receives a RS, it will multicast a router advertisement with network prefix to all nodes. After that, a node can calculate its IPv6 address by combining the network prefix and EUI64, which is calculated from the MAC address. Another scenario is that if an upstream router A, maybe it's an ISP, they give you a prefix with /40A, which assign in advance, like by email or a phone call. Then you can use them whatever you want in your LAN. Then here comes the link prefix and the routing prefix. First, the router B acts as a node on the interface. They link to the router A. Then router B asks router A for a prefix. The router A sends a /64 prefix for router B to calculate its own IPv6 addresses. Router B calculates an IPv6 address, let's say is 201:DBA:1, and use it on the interface that links with router A. So now router A can route all traffic to the address under /40A to router B. Now, when nodes want to get IPv6 and send RS to the router B just multicasts the /40A prefix to the nodes. Then the nodes can act as usual. So the functionality of the RA-DVD in the router OS should have two functionality. One is it can act as a node to receive RA, and it can multicast RA to the LAN. So let's follow the execution flow of RA-DVD to find the bug. The RA-DVD has a similar design pattern to the discover process we just mentioned earlier. It registers a callback check the socket in every loop. And if there is an incoming IC MPv6 packet, the looper call the registered callback. The callback do is roughly like this. In callback, it checks if the packet is a valid RA or a valid RS. If it's RA, then it stores information in handler 1, which is an A map. And if it's RS, it will multicast RA to its LAN. So there are 3 cases the router OS will multicast the prefix to nodes. First is when it receives the RS from the nodes. And the second is when it receives an RA from the upstream router. It will also immediately broadcast the RA to its node in the LAN. And the last one is router will multicast prefix in the default period, which is in 200 to 600 seconds. So yes, the router will multicast the RA to nodes once it receives a RA. But it's hard to trace this behavior directly, but because this is about the subscription, I'll talk about it later, but we didn't know the mechanism that time. So we didn't find why it did not send the RA while it received an RA. Okay. But the other 2 cases can be traced strictly directly and very easy. The RA-DVD call send RA right after it received an RS. The handler 1 registers a timer to send RA periodically. So we can find the send RA function by tracing these 2 methods. Following the send RA function, we found something interesting while the RA-DVD deals with the DNS advisory. It will advise DNS to nodes based on the DNS list it received from the upstream. The add DNS function is used to flatten the DNS tree and add it to the ICMPv6 row packet. The RA row is the ICMPv6 payload, which is a local variable with a size of 496 bytes. Okay, and let's step into the ADD DNS. And we can immediately find out there is probably a stack buffer overflow, just in plain sight. The function add DNS to packet by memory copy without any boundary check. That causes a stack buffer overflow if the DNS is big enough. But the DNS address are from the RDNSS of the RA packet. The max length of RDNSS of an RA is 8 bit, which is insufficient to override the return address. But if this is not the first time the router OS receives an RA, the RA-DVD has to expire all the RDNSS. Then makes the RA-DVD flatten another tree to overflow more bytes for us. So what we have to do is this. We have to act as a bad neighbor that sends a router advertisement with a big RDNSS list to the target router. Then send another router advertisement with a big RDNSS list. Now the return address is overwritten by an IPv6 address in the RDNSS of the first RA. And it's time to construct the exploit. And it looks easy because there's no protection enabled. And a thing to mention is the NX bit is not enabled just because the MIPS is not supported. So it's not their fault, just the chip's fault. Yeah. So let's find a way to jump on the stack and run our shellcode. That should be easy. Okay, the overflow IPv6 addresses are sorted since they were stored in a tree. To make the order of the IP addresses stable and ensure the shellcode is good, we can use part of the IPv6 prefix as a serial number and put a jump at the end of each address to jump over the prefix because they are not valid instruction. But because of the delay slot of MIPS, which means the instruction after the branch instruction will always be executed before the branch instruction itself. So we have to move the jump instruction forward. But the other problem is you cannot do a syscall in the delay slot. So basically, this is a bad idea. Okay, CTF 101 problem. Just make a prefix a valid instruction. They won't affect our gadget or shellcode. Then everything is fine. Yeah. And because we didn't leak any stack address, plus we didn't find any gadget that can be used to move stack pointer from register to SP to the register T9 for jump instruction in the first place. So what we did here is first write our own gadget on memory, then jump to the gadget. Finally, our shellcode will be executed. Sounds good, but there is iCache. Okay, the MIPS CPU has two caches, the instruction caches and data caches. While writing our gadget on memory, we are actually writing on D cache. Now, when we try to control the execution flow to execute the gadget for running our shellcode, the process first checks if the instructions are already in iCache. Because we wrote our gadget on the data section, the cache always misses, so the memory content will be loaded into iCache. They cause the processor to execute a bunch of nope until the program crashes. And to flush the D cache, we need to make process either context switch or exhaust the D cache. And the size of D cache is 32 kilobytes. There's no sleep in the RADVD. Other functions will also trap into the kernel, but they don't guarantee the context switch will always happen. So to make our exploit consistently successfully, to maximize the chance to win the game, we have to flush the 32 kilobyte D cache. And luckily, the value in randomized VA space of router OS is 1, which means the address of heap is not randomized. The only thing we need to do is to do some memory allocation to extend the heap and write some gadget on it. But let me run out of bytes for shell codes. Another but the DNS address was stored in a tree, and that costs a lot of memory space. So if you stop in the middle of this function, you will find that the heap is already larger than 32 kilobytes during the processing of a request. So we can call a memory copy by GOT hijack to write 32 kilobyte garbage on the heap to flush the D cache for our shellcode. Yeah, and profit. And this is the CVE 2023 32154. It was fixed, and after that, we found the vulnerable code has existed at least since the router OS v6. And the router OS v6 was published at the 2013. It means it has been 9 years. So it's 9 years until we found it, and after 10 years until they fix it, because they fix it after a year. And so my assumption was QED. Yeah, you're welcome. So combine this exploit with our exploit for the Canon printer for Pong2On. The attacking scenario is that an attacker is a bad neighbor of the MikroTik router, sending crafty ICMP-v6 to attack the router. And if we compromise the router successfully, we forward our payload to attack the printer. And the whole setup can be simplified as such in context. Just let our laptop act as an upstream router of the target router. So we can almost see our 100K bounty. Yeah, but our exploit only working on Mac OS and fail on Ubuntu, whether it's a VM or not. And the host of the ZDI will only run your exploit in the Ubuntu VM. So it must fail. We try to debug the exploit by running the exploit on Mac and recording the traffic, download traffic to Ubuntu, and replay it. Then it just failed as we expected. Yeah, that's normal. We also download traffic from Ubuntu and replay it on Mac, and then it succeed. What the fuck? So there's assumption. There must be an OS which is noted that we already order the packet. So we put a sniffer on the router to monitor the traffic from Mac and Ubuntu. And because the AF packet is not affected by any firewall chance, the result should be reliable, right? And they just look the same. So the last result could be I have to go to Toronto in person along with my laptop. But we can't leave it like that. Who knows if the bug will suddenly happen again during the contest, even on my Mac OS. So eventually, we found the problem. It's all about speed. The gap looks tiny, and you may never notice that in Wireshark. But the difference between them is actually 390 times. The problem is not on Ubuntu. It's just because the Mac sent to package too quickly, causing rest condition. And what will happen if you correct the how many bytes you want to write? Because we didn't calculate, we just smash some garbage on that and do some pattern matching, just like everyone did. So the solution is just put a slip between before sending the second RA and fix the offset of our payload, and that makes our payload very stable. The probability of success is almost 100%. Yeah, but how? The RADVD is only one thread. How could there be a rest condition? I didn't mention while the RADVD parsing the incoming packet, the DNS address are stored in a vector. But somehow, the handler passed a DNS tree to the add DNS function. What's the relationship between these two members? This is because we can't find, this is actually about why we can't find where the callback function multicasts the RA when it receives an RA packet from upstream. Let's look closely at the callback function. There is an array responsible for storing something called the remote object. Then it looks straightforward, just iter the new DNS vector and do MVRODNS on each of them and append result to DNS remote object vector. So what is the remote object? The remote object is a mechanism to store common resource in process, and other process can access them via ID. For example, a DNS remote object is actually stored in the handler 2 of the resolver, and the RADVD only preserves the ID of the object in handler 1. Now let's talk about the subscription in the Nova binary. The binary IP pool 6 is responsible for managing the IPv6 address pool. The DHCP described to it, so the DHCP can react to the change. It's done by sending a subscribe Nova message, and the sys notify CMD can specify which command you want to subscribe. The hex FE000B means notification. So if there is another binary, try to add an object to the handler 1 of the IP pool 6 by sending a Nova message, the 8 object of handler 1 will be executed. In most cases, the 8 object will call send notify to notify subscribers who subscribe to hex FE000B to inform them the IP pool 6 has changed. So when the RADVD receives RA from upstream router, it calls RODNS to create DNS remote object for each IPv6 address in RDNSS of RA. The command add object of handler 4 in the resolver is responsible for such request and will add an IPv6 object into the handler 2. Also, because the handler 1 of RADVD subscribes to the resolver's handler 2, the handler 2 will notify with every DNS address it has now. So the handler 1 constructs the RA for LAN with these DNS addresses. The problem is in the implementation of our DNS. Let's send over message by post message, which is non-blocking. It means the remote object won't get the object ID immediately. So if we send request too fast, the second RA arrives before the RA DVD gets the object ID of the old remote object. The RA DVD can only soft delete those old objects rather than really delete them. They cause the rest condition. So this is what happens if we follow them step by step. Because both processes are single thread, let's assume they are in the first loop of the looper while the RA DVD receives the first RA from when with one DNS address. The RA DVD creates a remote object in the resolver by sending a Nova message. And the resolver will set up a timer after receiving the first request because it cannot tell how many adding operations should be grouped as one. So it just set a timer and send only one notification when the time's up. Apart from notification, the resolver should send a response back to tell RADVD the object ID of the remote object it just asked for. But if we send the second RA quickly before the resolver sends the object ID back, the RADVD can only mark the old DNS remote object as destroyed. Then keep going to create DNS remote object for the RDNS in the second RA. Then we'll send a request to resolver, but as I said, we send the second RA too quickly. The resolver is still in the first loop, which try to send the object ID it created in the first loop. So our request will stay in the socket. Now the resolver sends the object ID back. The response handler is a callback function registered by the first request will handle the response. The handler finds out the object has already been marked as soft delete, so it won't update the object ID. Instead, it will post another request to the resolver to delete the object. The request will be processed in the third loop of the resolver after the request of creating the DNS remote object for the second RA. In the second loop of the resolver, it processes the creation request with the DNS address from the second RA and the response with object ID. Now, time's up. The timer of the resolver thinks a group of adding operations should have been done, and it's time to notify everyone what DNS addresses it has now. And because the handler 1 of RADVD subscribed to the handler 2 of the resolver, it receives the DNS addresses in the Nova message, then store them as a tree, and use them to construct the RA for LAN in the RA routine. At the moment, the result of 2 requests is missing. That's why our first version of the exploit can only work on macOS, because we trigger the rest condition. It seems hard to achieve rest condition because there is a timer, but the mechanism is more complex than I just explained. So the rest would always happen as long as 2 RA arrive at the router in a short period. So the pattern of a rest condition in the remote object is as follows. Use non-blocking method to create delete remote object, and the target process subscribe to the remote object. Then we can mix the result of 2 requests into one. They make us bypass some checks in the binary. So we try to find another vulnerability with this pattern so we could register the LAN category for the router in Pontoon. But we ran out of time and we modify our exploit like before the registration end 30 minutes ago. So we don't have time to find another bugs. So we failed to exploit the LAN side of the router OS. But at least we are the first team to exploit the Soho's mashup category successfully. And we also won the title of Master of Pong. But it's still sad that we didn't Pong the LAN. So summary. MikroTik re-implement everything with its own design IPC. The business logic is scattered all over. So one have to have a abstract concept of Nova binary to find the most critical code to reversing. And there is a pre-auth RCE on WAN that has existed for 9 years. Also, we introduced a pattern of race condition in remote object due to non-blocking method. And the last thing, we'll drop a tool we use in the point-to-one event to ease the reversing of router OS on GitHub. And I think it's really a good target for practicing the reversing engineering, especially with the limited time. You can read like every single line of the result of IDA, but it pushes you to like find critical part. Yeah, so I think it's really a good target. And thanks to ZDI, I paid the loan for my parent. Yeah. Any question?